Allumage Vulcain. Allumage EAP, décollage.
It was amazing.
I never thought I was going to feel so excited.
Yeah, it's always like that, pure adrenaline.
And social media are on fire.
Yes, yes. Let's post as well on the sister Twitter and Instagram. What do you think?
Copy. To Jupiter, but what do we know about Jupiter?
Jupiter, let's come here. Jupiter. Jupiter is the biggest planet in the solar system. It is 5 times farther from the sun than the Earth. The rest of the planets of the solar system could fit into Jupiter, even 2.5 times.
Yeah.
It's made of gas, mainly hydrogen and helium, like the sun. And if it were 80 times bigger, it could be a star.
Oh, wow. And Jupiter is the planet that spins faster in the solar system. A day in Jupiter is 10 hours, and year in Jupiter is like 12 Earth years.
Wow, great. I think it has around 60 moons. The biggest ones are called the Galilean moons because they were discovered by Galileo Galilei. And some are icy. Some of them are icy moons.
Yes, maybe. We could contact an expert on this.
Okay, let's call the Isaac
Yes.
experts.
So Jupiter is the largest planet of the solar system, and it has many moons. And the 4 biggest moons of Jupiter are called the Galilean moons, and they are called like this because they were discovered by Galileo 400 years ago. The 4 moons are, by order of distance to Jupiter, Io, which is quite small, extremely active, extremely volcanic, strongly affected by the gravity field of Jupiter, and this is the most volcanic object of the solar system. A bit further out, we have Europa, and Europa is actually very interesting in terms of astrobiology and with respect to the habitability. Because we have evidence that there are a subsurface ocean underneath the icy crust. And this ocean is actually in direct contact with the mantle underneath, which can be good conditions for chemical reaction to take place. Further out, we have the biggest moon of Jupiter, which is Ganymede, and Ganymede is actually also bigger than the planet Mercury. And it's a fascinating object because it has its own intrinsic magnetic field, so it has kind of a dipolar field, the same way than what we have on Earth, and this makes it like a very intriguing object. We also have strong evidence from previous mission that it hosts a subsurface water ocean. And even further away we have Callisto. Callisto is also a huge moon, but on the contrary to the other Galilean moon, it doesn't show any sign of present or past geological activity. However, previous mission also hinted that there might be an ocean underneath the surface of Callisto. So those 4 moons, despite being in the same neighborhood, present very different characteristics. And actually this is why many space missions are interested in going there and trying to characterize, doing some kind of comparative planetology between those different objects to understand how, despite being born in the same neighborhood, they have evolved so differently.
Hello.
Oh, hello. Welcome to our observatory.
Thank you.
a lot. How is the sun today, Antonio?
Quite active this week. Look at that sunspots.
Oh, wow. We are trying to get some data of Jupiter and its moons. Do you know how?
Maybe we can use the 3D models from Seyfried so we can see Jupiter
Yeah.
and the Galilean moons.
Oh.
Let's do that.
Yes. Antonio, what are you doing?
I'm assembling this used 3D model. Do you like it?
Yes, sure.
You can also download it from SciFleet webpage and print it with Caesar's 3D printer.
Oh, nice. And do you know what is each part?
Actually, I don't.
Why don't we call the ISAC experts on yours?
Oh, great. Let's go.
So you see here our JUICE spacecraft, which was launched on April 14th of this year, 2023. It's a 1/10 scaled model, so you have to imagine it's much bigger in reality. It weighs about 6 tons, and it's really huge in size. So we need 80 meters square of solar panel to generate all the electricity we need at Jupiter. So actually, on each side of the spacecraft, you have a 15-meter long solar panel. So this is a quite typical space probe. You see here the so-called Huygens antenna, which will send all the data acquired in the Jovian system to Earth. And you see that on this side, all the instruments, or most of the instruments, let's say the optical instruments, are located in order to all be looking in the same direction when we will be pointing the spacecraft at one of the Galilean moons.
So, Carlota, the JUICE experts were saying that the JUICE trip will take around 8 years and that they will be around 4 years studying Jupiter and the icy moons.
Yes, exactly. And Bea, I don't know if you know, but JUICE is going to use the gravitational assistance of Venus and the Earth to arrive to Jupiter.
Yes, this is a great idea. So they need less fuel.
Exactly.
And so if imagine we want to derive the orbit or the trajectory of JUICE around Jupiter. Maybe we can consider, the main values there are G times M, being G the gravitational constant.
And M, the mass of Jupiter.
Sure.
So to calculate it, we can use Stellarium.
Yes, great idea. So for example, from the orbital movements of one of the moons or all of the moons, we can derive the mass of Jupiter.
Exactly.
Okay, let's do that.
I'm done with the calculus of the mass of Jupiter.
Me too.
Great. And maybe we can check it graphically?
Yes, using cosmographia, I think we can check the orbit of JUICE.
Yes, and why don't we contact the space experts on cosmographia?
Let's do that. Do you call them?
Yes.
Hello, my name is Alfredo Escalante. I work at the European Space Astronomy Center here in Madrid, Spain. And especially I work for this space service. Our main goal is to provide geometric information to scientists in order to analyze the different scientific observations of the spacecraft that we have around the solar system, like BepiColombo, Mars Express, and JUICE, the Jupiter Icy Moon Explorer that was launched in April. And today I'm going to show you a very interesting, very nice application, which is called Cosmographia. It's also public and free to use, so feel free to use it. And it's this very nice 3D visualization application which allows us to visit in 3D all the bodies in the solar system, so we can go to all the planets, the moons, asteroids, comets. And in this case, I'm going to show you a brief example of visualizing the orbit of a spacecraft or any body, orbiting, in this case, Jupiter. And we'll see the effect of changing the mass of the central body and how these different mass will affect the orbit of the spacecraft, which is actually orbiting. Okay, so as you can see, we are now in Jupiter. So here we can see the 4 Galilean moons, Callisto, Ganymede, Europa, and Io. And these 4 moons have a very circular orbit. So we'll take an example, a spacecraft which is orbiting Jupiter with a circular orbit. So we have the position and the velocity measured in a very similar orbit to Callisto, for example. But then what could happen if we double the mass of Jupiter for the same initial conditions of position and velocity? So as you can see, now the orbit is much more elliptical, and the pericenter, the distance closest to the planet, is now much closer to Jupiter. This is because Jupiter is acting like a sink. So as the mass of Jupiter increases, the gravitational pull also increases. And if we increase the mass of Jupiter instead of 2 times by 20 times, we get to this highly elliptical orbit that, as you can see, it's even leading to crashing into Jupiter. On the other hand, if we reduce by 20% the mass of Jupiter, what we get is this circular orbit, but very eccentric, which means that Jupiter, as you can see, is not in the center of this orbit. So this is another effect of having lighter mass. So what we have just seen is a very graphic example of the application of Newton's gravitational law, in which for a very small body, in this case the spacecraft, which is orbiting a very large mass, in this case Jupiter, for a given initial conditions of position and velocity, the orbit of the spacecraft only depends on the mass of the planet. And this leads, of course, the higher the mass, the higher is the gravitational pull, so we get closer to the planet. On the other way around, the lighter the mass, the lighter the planet, we get farther away from it for the same initial conditions on position and velocity. And this very nice example is just one of the nice things that you can do with cosmography.
Did you enjoy this challenge?
Now you know what you have learned in class, how it's used in STEM professions.
And how scientists work here at ISAC, scientists and engineers.
Yes, so stay tuned because we will show you more challenges soon.
And follow us on Twitter, Instagram, YouTube. Thank you. See you.
Thank you. See you soon.